Hey guys, so I have tons to get through today. It was a very long chapter for this week, and then also the problem set from last week. So it's going to be split up into a lot of different videos, and actually, this week is actually really conducive to that, because this lesson was actually already broken up kind of into 4 different portions, or a couple different portions. So we'll be really dealing with transformations and equations for that and thinking about that geometrically and in space. Kind of continuing on from last week. And the first thing that I wanted to start with was orthogonal projections. So I wanted to first explain to you what an orthogonal projection was. So an orthogonal projection would be, for example, if you had something like this, where you start out with vector 0, 2 and vector 1, 0. And if you multiply by some matrix B 1, 0, 0, 0, and what you ended up with was just the 1, 0, meaning this this thing was orthogonally projected onto the horizontal axis. So that would kind of be, that would kind of be like the most basic idea of what an orthogonal projection is. And I just kind of wanted to show you that so you have an idea of what we're talking about here. So that's the first transformation that we're going to talk about. So we're really going to look at what this looks like. So we'll start out with this image. If we've got a drawing here where we've got vector x is this line, the vector parallel, or the vector x that is parallel to line L, this would be line L here, and then the vector x that is perpendicular to line L. And you should probably already know this from like geometry and stuff, but when we have these two lines, it means parallel and this means perpendicular. Right, okay, so if we start out with this idea, we've got a vector x, we've got a line L, something that's parallel to line L, something that's perpendicular to line L. We're going to think about an orthogonal projection that takes this x and puts it on this line. Okay, so the first thing that we could say is that x can be written as x can equal vector, the parallel vector plus the perpendicular vector. And I mean, that's pretty easy to visualize. Let's see. Yes, this marker works. Because, if we think about it, if we like add these two things together, we're gonna get that. A way that we can think about that would be the Pythagorean theorem, a squared plus b squared equals c squared. So if we know that that's true, then what we can say is that, say we've got, we're just going to write this out in formal terms just for the sake of it. We've got a transformation T of vector x equals this, right? Because, if we're transforming it onto this line, right? From R2 to R2, right? So the orthogonal projection of x onto L. The way that we want to write out an orthogonal projection formally would be projection, this is short for projection, onto L of vector x, which we would say equals this. This is the basis that we start of. What we're trying to figure out basically is the matrix that we would use, like a general rule for the matrix that we would use to find the orthogonal projection. So we're going to use a bunch of rules and logic. So if we know that this is parallel to this, and what I mean by that is that if we write another line out and call it L perpendicular, we've got L here, line L, and this would be the line perpendicular to it. So in other words, the vector x perpendicular to L would be parallel to the line perpendicular to L, right? So that's the first thing we need to know. And then we know that if we write this out, that equals an orthogonal projection of x onto L, right? Because if we had take x, the same can be said, if we know that this would be an orthogonal projection of x onto L, then this would be an orthogonal projection of x onto L perpendicular, right? And I'm pretty sure the book really just showed us this to make sure we understood the idea that we're dealing with here of how orthogonal projections work. But what we're going to do is we're going to use the dot product formula to figure out the matrix for orthogonal projections. So first thing we need to know. So we already know that this equals the projection of L onto L of x, right? Well, we can say that this is equal to k times vector w, where vector w is a non-zero vector parallel to L, right? So if we know that, we can say that the perpendicular vector x is equal to vector x minus parallel, which is in turn equal to x minus k w, right? So we know that vector x minus k times vector w equals this perpendicular line here, right? If we're trying to find the dot product, then the other thing we need to know is the parallel line, right? And that would just be w, right? Because that's on this line. So if we were going to write out the dot product or perpendicular dot product, so where it equals 0, then we would just have x minus k w times w equals 0. Now here's where we can do some nice little distribution and mathy stuff. So if we distribute the w, to both places, then we end up with vector x times vector w minus k times vector w equals 0. Then we can extrapolate out here, say that k equals vector x times vector w over vector w times vector w, right? That's what k would equal. So what we can do is say that now that we know what k equals, we can say that if the projection of L onto x equals the parallel vector minus equals the parallel vector, well, then the parallel vector equals k times w. Well, we now know what w is, or what k is. So we've got x times w over w times vector w equals this projection, right? Now, you might be like, what are we going to do with that? That's a bunch of numbers. What we can do is simplify it using this really handy dandy trick called the unit vector. So I'll do this in a different color to make it a little bit simpler, but a unit vector. This is going to be used a lot throughout the chapter. The basic idea is it's this vector u. And the vector u, if you take the length of vector u, it equals 1. And if I haven't already pointed this out before, or I don't point it out in other videos, the way that you're going to take the length of a vector is you're going to do the square root. It's just the distance formula. I actually did point this out in a couple other videos, but if you did not think to extrapolate it to this, it's the distance formula. You've got like u1 squared plus u2 squared plus u3 squared, on and on and on, square rooted, and that is your distance formula. So when we do these two little lines on either side, that's asking for the distance, for the length. And a unit vector is where the length is 1. So you can use the unit vector to simplify an equation like this and make it a little simpler to see and to use. So what I'm going to do is take this and say that if we've got a unit vector u parallel to L, which means that it would be taking the place of this W, right? Then we can say, okay, we can say vector X times vector U over U times U times vector U. And what we can do here is we can simplify that, because what we know is that these two, if they both equal 1, 1 times 1 is 1, right? And any fraction over 1, it's just, we can just get rid of the denominator. So what we can end up with is just this, okay? So we can then say, I'm going to erase all of the work that we've done up to this point, but just leave this part, because that is what is important, is that we've now gotten to this place of the vector X times vector U times vector U equaling the projection, okay? So we know this. What can we do with this now? So what we're going to say now that we know this is that if, so the problem the book asks us is T of X equals projection onto L of X linear? And if so, what is the matrix? So, if you remember at the beginning of the video, I said, we're trying to figure out the matrix that we can always use, a general matrix that we can always use in orthogonal projection problems. So what we're going to start out with is we know that in this case, X is X1 and X2, and U is U1, U2. So if we take this idea, this equation right here, well, we can write it out pretty simply, because we can just say X1, X2 times U1, U2 times U1, U2. So if that's hard for you to visualize, basically I took these vectors and I wrote them out, breaking them down into their actual components. So once we've got that, I'm not going to go through the whole process, because I think we've all, practiced this. It's basic. But if you multiplied all of these things, then what you would eventually get is the matrix U1, U1, U2, 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 U2 times vector X. So you get this matrix. Okay. So here is where I'm going to have to, there was a lot of content covered this week. So I was not able to ask all of the questions that I wanted to ask of Dr. Prudhomme. So there are a couple points in this chapter that I'm going to be honest are still things that I have to talk about. So I might not be able to fully explain. So one of them is coming up right here, which is that they took this idea of these unit vectors, and they kind of converted it back into a general equation with W that didn't have the unit vectors. And what they did was they took this and they ended up with the matrix P equals 1 over W1 squared W2. So basically just like the same thing as here, but with W, and then they had this extra little operation here. I'm pretty sure, it has something to do with converting from unit vectors back into just like any arbitrary vector, but the book did not go into detail on that. So that is something that I will bookmark for myself to remind myself to bring up in a future video. But what's really important here to know is that this is the general matrix formula that we are going to use for or is that this is the general matrix formula that is the W version of the unit vector idea right here. But really all you actually should know is this vector. And this is a general vector where we can use this for, anytime that we have an orthogonal projection, we just use that matrix, right? Or that matrix, which is helpful to know. So I'm going to stop my first video here, but this is the basic format that I'm going to follow for the next few videos, which is presenting a transformation and then going through the steps in the proof to explain to you why, to explain to you what the matrix is that we would use to find this certain type of transformation. The last thing that I will do is very quickly write out a summary of like the proof for this, which is really just a summary of what we did. So actually it's a definition in this case, but any vector x in R2 equals parallel and the perpendicular. That's like the first thing we talked about. If vector W equals non-zero parallel vector to L, then we have this thing going on here. I already sort of explained. If the unit vector equals U1, U2, then the projection onto L of x going to equal the vector x times the vector u times the vector u. Transformation T of x, vector x equals projection onto L of vector x equals linear with the matrix P equals 1 over this that I already drew out before, which is also equal to the unit vector version of this. Okay, so this is really the summary of everything you need to know in this one big definition here, and this is for any orthogonal projection. Okay, so you can pause the video if you want to like look at this and try to figure out if there's anything else that you didn't understand, but I'm going to stop it here. I'm going to come back with reflections.